So oftentimes when you have a integral with respect to both dx and dy, there's a way to simplify it down by checking if it's independent on path. This is where we split the two sections, dx and dy, into p and q, and then doing the delta p delta y, so partial derivative of p with respect to y, and the partial derivative of q with respect to x, and seeing if they're the same. So to do that here, delta p delta y, this stays the same here, plus 1, that becomes 0, so delta p delta y equals 2x ey. Then for q, partial derivative with respect to x, this 2 comes on the side, so it's 2x ey. Then the cos y, that becomes 0, so we have 2x ey as well. So delta p delta y equals delta q delta x, they're the same, so we can say it's independent of path. So for the next part, it's a bit hard to understand kind of why we're doing all of this, but you kind of follow the steps of how to do it, and then it all makes sense later. So what essentially we're trying to find is u, which is basically kind of a simplified expression that if we were to kind of find the difference of it with respect to the two limits, then it would essentially give us the answer to this integral. Instead of having to do this long integral by itself, it simplifies it down. So in order to do that, we start with p, do the partial integral with respect to x, then the partial derivative of that with respect to y, and then compare that to q, which sounds a bit weird, but it will make sense shortly. First step, as I said earlier, is to start with p, and then do the partial integral with respect to x. So this 2x ey becomes x squared ey, the 1 just becomes an x, and then instead of having an integration constant afterwards, we have a function in terms of y, because there's only a partial derivative with respect to x, so we need to kind of factor in the y here. So now this gives us u, but the problem is this function is unknown. So we're going to compare what we have with q in order to hopefully kind of get a function. So this u, do the partial derivative with respect to y, would give us x squared ey plus f dash y, because the derivative of f of y is equal to f dash y. So in order to find this f dash y, we have to compare this to what we have for q. So remember that q from the last page is equal to x squared ey plus cos y, and what we have here is x squared ey plus f dash y. So this is the same, that's fine, but then f dash y, we see that the counterpart is cos y. So you can say that cos y equals f dash y, and then to find f of y, we do the integral of this, so we have sine y. So now putting this into what we have earlier for u equals x squared ey plus x plus f of y, so that f of y is sine y, so that means that u is equal to x squared ey plus x plus sine y. Now that we have u, essentially all we have to do is evaluate the difference between u for the value of b minus u for the value of a. I'm just using a place marker, but whatever would be the two limits.